Hi, my name is Daniel Sandoval Marquez. I'm a PhD student in Nanotechnology Engineering at Tecnológico de Monterrey, Campus Estado de Mexico, and I'm going to be presenting this project that we developed during my undergraduate studies, called Sustainable Development of Value-Added Composites through the combined recycling of multilayer plastics and medium density fiberboard residues. Now, what is this project about? Let's start with our key problems. Multilayer plastics account for 39% of overall packaging, of which a very small percentage is actually recycled. There are several routes for recycling, chemical and mechanical. Chemical recycling techniques are often or too expensive and or inefficient, while mechanical recycling is actually promising, as there is a lot of infrastructure around from companies that deal with plastics. However, when introduce multilayer plastics as fillers, even with compatibilizers, they often tend to result in lower mechanical properties. What is our proposed solution for this problem? Let's take a step back and add a little bit of context. Wood plastic composites, or WPCs, have been used to improve mechanical properties of either wood or plastic in different percentages. Young modulus, flexion, impact strength, and many other mechanical properties have been reported to improve considerably in these composites. However, there is no study of the introduction of wood fibers in one composite that has a polymer matrix and multilayer plastic as fillers. So the working theory is that the wood fibers are going to counteract the negative effects of the MLPs, in our case in a high-density polyethylene matrix. Now let's pass on to the methodology. We develop 5 different plates with varying degrees of polyethylene, multilayer plastics, wood fibers, compatibility, in this case PTW from Dow, and calcium carbonate. The first one is going to be our blank, pure HDPE. The second one is going to have multilayer plastics and compatibilizers, 10% and 10%. The third and fourth are going to have varying degrees of multilayer plastics, 5, 10, and 20%, a fixed percentage of wood fibers, and compatibilizers, 10 and 10%, and a fixed percentage of calcium carbonate, 5% in this case. The wood fibers were treated with maleic-anhydride in order to improve the interfacial adhesion. Now, how did we process these blends? First of all, our raw matter. Our raw matter was obtained from HDPE 4710 recycled from pipes from impact testing as our raw materials. These pipes were never in use, so they are relatively new. These pipes were shredded, extruded, and pelletized into pellets where they were prepared with the rest of the blends. These blends were extruded, pelletized again, and passed through an injection molding process in order to obtain 4 different specimens. A tensile test specimen, impact testing, and 2 miscellaneous ones. Now let's start with our results, in this case the FTIR. With the wood treatment, we didn't see very much of a difference in the structure of the wood fibers. However, there is a small shift that indicates that there are certain bonds that was made that may improve the interfacial adhesion. That in the next slide we are going to see that in fact the interfacial adhesion is almost perfect, but let's wait a little bit. And from the other elements, the multilayer plastics, the compatibilizer, the calcium carbonate, all have presence on the different blends, except obviously from the blank, and partially on the PMC10, that is the one that has the multilayer plastics only. Now let's pass on to morphological analysis that was made through SEM into tensile test specimens and cryogenically fractured specimens. For me, in my opinion, this is one of the most important ones, as it describes almost everything in the next slides. Let's start with the integration of wood. The integration of the wood fibers is almost perfect. There is a seamless transition in between the polymeric matrix and the wood fibers, indicating that the treatment in fact worked very well. In contrast, the multilayer plastics did not have any integration at all, generating microcavities and inducing stress concentration points that are going to lower the mechanical properties of our composites. These stress concentration points reduce the elongation percentage, the toughness, and ultimate tensile strength of our material. However, it increased the stiffness of the material. Young modulus, resilience, and yield strength improve with this. Why did this happen with the introduction of more multilayer plastics? Mainly because of the presence of the PET and polyamide present on the multilayer plastics. These have a higher stiffness relative to the polyethylene, so it makes sense that they are increasing as we add more and more multilayer plastics. Sharp impact strength also decreased due to the presence of these stress concentration points. On the other hand, short hardness and the negative effects of that the multilayer plastic had on it were counteracted by the presence of the wood fibers, as medium density fiberboard has a far higher hardness than any plastic on the blend, so at lower levels it was counteracted. Another characterization technique that we applied to our blends was MFI, or melt flow index, that is going to describe how much of a material flows in a certain period of time, in this case grams per 10 minutes. Our base material has a very low MFI of 0.1, being very low for standards of plastics. However, it does make sense as its precursor is a pipe that needs a very low MFI for its extrusion process and fabrication. Now, about the water absorption rate, we can see a very expected result. With the presence of wood fibers, we can see an increase on water absorption rate. But why does this happen is very interesting. Yes, the wood fibers are absorbing water, but they are also forming a porous phase on the polyethylene matrix. This porous phase allows water to penetrate and reach previously encapsulated multilayer plastic that they did not previously interact with water, increasing with the multilayer plastic percentage the rate. Now, going to our last characterization, in this case DSE, or differential scanning calorimetry, we can observe a lot of information about the formation of our material. Let's start with crystallization temperature. This slight increase is going to indicate an increase on the restriction of the polymeric chains. This restriction increases the stiffness of our material. On the other hand, the slight changes on the melting temperature are an indicator of a reorganization of the crystal structure and the lamellar thickness of the material. Now, talking about the crystallization percentage, we can observe two opposite behaviors competing with each other. The first one is the polymer chain restriction that reduces crystallinity. An opposite effect to that is the nucleation effect that the calcium carbonate, the multilayer plastics, and at a certain degree the wood fibers have on the polymeric matrix, being this more pronounced at higher multilayer plastic percentages, such as at 20%. Let's end this presentation with our conclusions. First of all, the mechanical properties were not as good as we expected. However, the wood fibers did fulfill its function of counteracting most of the negative effects of the multilayer plastics. We will learn that certain properties of the multilayer plastics can be beneficial to a composite. However, we still need to learn how to tweak the interfacial adhesion, either through the use of a compatibilizer, the process conditions, or a treatment such as the one used with the wood fibers, that these were very good to the point that there is a perfect interfacial adhesion. So tweaking these conditions could lead to a far better composite. These composites also introduce another route of recycling for multilayer plastics, increasing the circularity of the material. In a specific application, we still haven't done an economic viability evaluation. However, we can infer that a high stiffness, low impact scenario could be ideal for our material. And that would be all for my part. I would like to thank my lab partners and assessors Ariana Carmona, Emiliano Guevara, and the doctors Ulises Figueroa y Andrea Guevara. Thank you so much, and you for hearing me out.